The morning of April 8, 1941, dawned clear over Kagamigahara Airfield, 60 kilometers north of Nagoya. Major Kazuyuki Saito stood on the tarmac, watching as ground crews made their final checks on the massive aircraft before him. The Nakajima G5N Shinzan Deep Mountain represented 3 years of clandestine work, countless engineering hours, and Japan's most ambitious attempt yet to build what its military leadership believed it desperately needed, a heavy bomber that could strike across vast Pacific distances and match anything the Americans might field. What Saito couldn't know, as he prepared to observe the aircraft's maiden flight, was that he was watching the beginning of a failure so complete it would expose a chasm in industrial capability that no amount of courage or determination could bridge. The Shinzan would never become the weapon Japan needed. Instead, it would become something far more valuable to history, evidence of the precise moment when Japanese engineers discovered that replicating American industrial achievement required more than blueprints and willpower. It required an entirely different approach to manufacturing, metallurgy, and mass production that Japan simply did not possess. The aircraft before Saito looked impressive. With a wingspan of 138 feet and stretching over 100 feet in length, the Shinzan dwarfed everything else on the field. Its 4 radial engines gleamed in the morning sun. Its aluminum skin had been meticulously riveted by some of Nakajima's finest craftsmen. To anyone watching, it looked like the heavy bomber the Imperial Japanese Navy had commissioned. But appearances, as Saito and his engineering team would soon discover, concealed fundamental problems that went far deeper than any superficial inspection could reveal. This is the story of how Japan tried to build its own B-17 flying fortress, and how the spectacular failure of that attempt revealed a truth more devastating than any battlefield defeat, that the Pacific War would not be decided by the courage of pilots or the skill of admirals, but by the grinding, unglamorous reality of industrial capacity, material science, and manufacturing techniques that some nations possessed and others did not. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. To understand why the Shinzan's failure mattered so profoundly, you must first understand what Japan believed about itself in 1941. The Imperial Japanese Navy had spent decades building a military force designed around a specific strategic vision, intercepting and destroying the American Pacific Fleet as it steamed westward across the ocean. This strategy required long-range aircraft that could scout ahead of the fleet, locate enemy vessels, and strike at them from distances that would keep Japanese carriers and bases safely out of reach of American retaliation. Japan's twin-engine bombers, the Mitsubishi G3M, and its successor, the G4M, had proven this concept's value. Fast, long-ranged, and capable of carrying torpedoes or bombs, these aircraft had achieved remarkable results. In the opening days of the war, G3M and G4M bombers would sink the British battleship Prince of Wales and the battlecruiser Repulse off the coast of Malaya, the first time in history that capital ships underway at sea had been sunk by air attack alone. To the Japanese naval staff, this seemed to validate everything they believed about aviation's role in modern naval warfare. But there was a problem that became apparent to more thoughtful strategists even before the war began. Twin-engine bombers, no matter how well designed, had fundamental limitations. Their range, while impressive, wasn't unlimited. Their bomb load was constrained by the physics of 2 engines, and most critically, they were vulnerable. The G4M's lack of armor and self-sealing fuel tanks would earn it the grim nickname the Flying Lighter from Allied pilots, who discovered that a few well-placed rounds could set one ablaze. The solution seemed obvious. Japan needed 4-engine heavy bombers, aircraft that could fly farther, carry more ordnance, and possess the structural strength to absorb battle damage and bring their crews home. Aircraft like the American B-17 Flying Fortress that was already in service, or the B-24 Liberator then under development. Japan's problem was simple to state but immensely difficult to solve. Japanese aircraft manufacturers had never successfully designed, built, and operated a four-engine heavy bomber. This wasn't for lack of trying. Various proposals had been floated throughout the 1930s, but each time the projects foundered on the same fundamental obstacles. Japanese industry lacked experience with such large, complex aircraft. The engines required each needing to produce well over 1,000 horsepower reliably for hours at a time, pushed the limits of Japanese engine design. The airframe structures needed to carry heavy bomb loads over long distances, required manufacturing techniques and quality control that proved elusive. So in 1939, the Imperial Japanese Navy made a decision that seemed pragmatic at the time. If Japan couldn't design a four-engine heavy bomber from scratch, they would copy one. Not openly, of course, that would have been diplomatically impossible in the years before the war, but through a transaction that had plausible deniability. The Mitsui Trading Company purchased the Douglas DC-4E, an American four-engine airliner prototype that Douglas Aircraft had been unable to sell to any American airline. The DC-4E was a remarkable aircraft in its own right. Douglas had designed it as a pressurized transcontinental airliner capable of carrying 42 passengers in considerable luxury. It was large, sophisticated, and represented the cutting edge of American commercial aircraft design in the late 1930s. It was also, critically, a financial failure too expensive, too complex, and too ambitious for the conservative airline industry of the time. To Douglas Aircraft, selling the sole prototype to a Japanese company for $950,000 was a way to recoup some of their development costs. To the Japanese, it was an intelligence windfall. The aircraft arrived in Japan by ship in September 1939 and was immediately turned over to the Nakajima Aircraft Company with instructions that were both simple and impossibly complex. Study everything about this aircraft and use that knowledge to design a long-range naval bomber. Teams of engineers descended on the DC-4E. They measured every dimension. They photographed every structural member. They created detailed drawings of the wing spars, the fuselage frames, the engine mounts. They examined the control systems, the hydraulics, the electrical systems. For engineers who had never worked on an aircraft of this size and complexity, the DC-4E was like a textbook come to life, showing them not just what needed to be done, but exactly how American engineers had solved the 1,000 small problems that arose when building something this large. The aircraft was then officially lost in an accident in Tokyo Bay, a convenient cover story to explain why it had vanished from public view, while teams of engineers continued their exhaustive analysis at Nakajima's facilities. For nearly 2 years, engineers studied the American airliner, learning its secrets, translating American approaches to Japanese manufacturing techniques, preparing to create their own version adapted for military use. And this is where the story becomes instructive, because what happened next reveals something profound about the difference between copying a design and understanding the industrial ecosystem that created it. When Nakajima's design team, led by Chief Engineer Katsuji Nakamura, began translating their studies of the DC-4E into plans for a military bomber, they made what seemed like reasonable decisions. They kept the DC-4E's basic configuration: mid-wing monoplane, 4 radial engines, tricycle landing gear. They maintained similar dimensions and used the wing and landing gear designs almost unchanged. These were proven solutions to the aerodynamic and structural challenges of a large 4-engine aircraft. But they also made changes that any military engineer would consider necessary and proper. They modified the fuselage to include a bomb bay, add defensive gun positions, and incorporate military equipment. They replaced the civilian engines with the Nakajima Mamori 11, a powerful 14-cylinder radial designed to produce 1,870 horsepower, nearly equal to the best engines then available to American manufacturers. On paper, these changes made sense. In practice, they created cascading problems that would doom the entire program. Because what Nakajima's engineers didn't fully appreciate was that the DC-4E was already a borderline failure. Douglas had abandoned it precisely because it was overweight and underpowered. The Japanese modifications, seemingly modest, added approximately 20% to the aircraft's weight, 20% heavier than a design that Douglas had already concluded was too heavy. The result was the G5N Shinzan, the aircraft Major Saito watched on that April morning in 1941, and from its very first flight, the problems were apparent. The aircraft was sluggish, struggling to reach altitude with its test load. The Mamori engines, running at high power settings just to lift the overweight airframe, ran hot and showed troubling signs of unreliability. The flight characteristics were poor. The aircraft felt mushy and unresponsive, difficult to control with precision. Test pilots filed detailed reports. The Shinzan's maximum speed was disappointing, well below what the specifications had called for. Its range, while respectable, fell short of requirements. Most troublingly, the complexity of the design created maintenance headaches. Systems that worked reliably on the American airliner proved finicky and difficult to service when adapted for military use in the Japanese context. Engines that were supposed to be the most powerful ever fitted to a Japanese aircraft instead revealed themselves as temperamental and prone to failure. Nakajima built 3 more prototypes, hoping that modifications could salvage the program. Engineers strengthened some structures, lightened others, adjusted engine settings, modified control surfaces. Nothing helped enough. The fundamental problem wasn't any single design flaw that could be fixed. It was that the entire aircraft was a marginal design pushed past its margins by the modifications needed to make it a military bomber. In desperation, Nakajima built 2 more airframes and fitted them with different engines, the Mitsubishi Kasei 12, producing 1,530 horsepower. These engines were proven and reliable, already in use on the successful G4M bomber. Perhaps more reliable engines would solve the Shinzan's problems. Instead, they made everything worse. The Kasei engines produced less power than the Mamori engines they replaced, which meant the already overweight and underpowered aircraft was now even more underpowered. The aircraft that resulted could barely maintain altitude with a full load. By mid-1943, after 2 years of effort and the construction of 6 aircraft, the program was cancelled. Not officially cancelled, that would have been too great an admission of failure, but quietly redirected. The 6 Shinzan aircraft were converted to long-range transports, stripped of their military equipment and assigned to a transport unit. They would spend the rest of the war hauling cargo and personnel, a task for which they were adequate but hardly exceptional. The official explanation for the Shinzan's failure focused on technical problems: unreliable engines, excessive weight, complexity of maintenance. But some of the engineers who had worked on the program understood that these surface explanations concealed a deeper truth. The real problem wasn't that Nakajima had failed to copy the DC-4E correctly. It was that they had succeeded in copying it too well, replicating an American aircraft without also replicating the American industrial and material science foundation that had made such an aircraft possible in the first place. Consider the engines. The Mamori 11 was, on paper, comparable to American radial engines of similar size and power output. Japanese engineers could measure its horsepower, its displacement, its dimensions. What they couldn't easily measure or replicate was the metallurgy that went into its construction. American engines used alloy steels and specialized aluminum alloys developed through years of research and industrial trial and error. They benefited from manufacturing tolerances that could be held consistently across thousands of engines because American factories had invested in precision machine tools and quality control systems. Japanese engines, built with the materials and manufacturing capabilities available to Japanese industry, looked similar and tested similarly when new. But they wore differently, failed differently, required more frequent maintenance, and had shorter service lives. An American engine might run reliably for hundreds of hours between overhauls. A Japanese engine of similar design often needed attention after half that time. Multiply this difference across 4 engines, and an aircraft that was marginally acceptable with American engines became unreliable and maintenance-intensive with Japanese ones. Or consider the airframe structure. The DC-4E used aluminum alloys, developed by American materials scientists, alloys with specific strength-to-weight ratios and fatigue characteristics. Nakajima could measure the dimensions of every structural member, could create drawings that precisely replicated the American design. But when they built those structures with the aluminum alloys available from Japanese suppliers, they got structures that were heavier for the same strength, or weaker for the same weight, or more prone to fatigue, cracking, or all 3 at once. These weren't huge differences, perhaps 5 or 10% variations in material properties. But in aircraft design, margins matter enormously. A structure designed to operate with a safety factor of, say, 50%, meaning it could handle loads 50% greater than normal operations would impose, might work perfectly well with American materials. Built with Japanese materials that were 10% weaker, that same design now had only a 35% safety margin. Still, adequate, perhaps, but now much more sensitive to any additional weight or stress. And this is what happened to the Shinzan. A design that was already marginal with American materials and manufacturing became hopelessly inadequate when built with Japanese industrial capabilities. The 20% weight increase from military modifications pushed the aircraft past the point where Japanese industry could support it. The result was an aircraft that didn't fail catastrophically. The wings didn't snap off, the fuselage didn't break apart, but that failed in a more insidious way. It simply didn't work well enough to be useful as a frontline combat aircraft. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. But the story of Japan's attempt to build a heavy bomber doesn't end with the Shinzan's quiet relegation to transport duty, because in early 1942, as Nakajima was, still struggling with the Shinzan's problems, Japanese forces in the Philippines captured something far more valuable than any set of blueprints: actual B-17 flying fortress bombers. When Japanese aircraft attacked Clark Field in the Philippines on December 8, 1941, December 7 in Hawaii, and the same day as Pearl Harbor, they caught American forces by surprise and devastated the B-17 force stationed there. Most of the flying fortresses were destroyed on the ground or so badly damaged they could never fly again. But in the chaotic fighting that followed, as American forces retreated south through the Philippines and then to Java in the Dutch East Indies, several damaged B-17 seconds were abandoned. Japanese salvage teams found at least 3 B-17 seconds that could be restored to flying condition. One was a B-17D model, an earlier version of the type. 2 were B-17E models, more recent and sophisticated. These aircraft, remarkably, still contained their top-secret Norden bomb sights, the devices that American crews were supposed to destroy rather than let fall into enemy hands. Through early 1942, Japanese engineers and captured Allied mechanics worked to restore these aircraft to flying condition. Parts were scavenged from other wrecks, systems were repaired, engines were overhauled. And then, in mid-1942, these restored B-17 seconds were carefully flown to Japan, escorted by fighters and with anti-aircraft batteries along the route, warned not to shoot at the American bombers now bearing Japanese markings. At Tachikawa Airfield near Tokyo, Major Saito and a team of engineers from the Imperial Japanese Army Air Force's Air Technical Research Institute took possession of what they had been told were 3 of America's most advanced bombers. Their assignment was straightforward: evaluate these aircraft thoroughly, discover their secrets, and determine how Japan might counter them or replicate their capabilities. What followed was an engineering education that would prove both enlightening and dispiriting. Over the next 2 years, Japanese test pilots and engineers flew the captured B-17 seconds extensively. They measured performance, speed, range, altitude, bomb load capacity. They studied the defensive armament, the number and placement of machine guns, the fields of fire, the vulnerabilities. They examined the structure, how the wings attached to the fuselage, how the bomb bay was designed, how the flight controls operated. They even used the aircraft in training films, teaching Japanese fighter pilots how to attack B-17 seconds effectively. Every measurement and test flight revealed something about American engineering and industrial capability. The B-17E, the newer model, could carry nearly 4 tons of bombs, more than 4 times what a Japanese twin-engine bomber could manage. Its maximum range exceeded 2,000 miles. It could fly at altitudes where Japanese fighters struggled to operate effectively. Its defensive armament, with 50 caliber machine guns in multiple positions, made it dangerous to attack from any angle. But more revealing than the aircraft's performance specifications was what Japanese engineers discovered when they examined how these machines were actually built. The quality of the aluminum alloys, consistent and reliable. The precision of the manufacturing, with parts that could be swapped between aircraft with minimal fitting and adjustment. The sophistication of the systems, electric turrets that could track targets with unprecedented precision, oxygen systems that allowed the crew to operate at high altitude, communications equipment that worked reliably. And most tellingly, the sheer number of parts involved, each manufactured to high tolerances, and the complexity of coordinating that manufacturing across multiple factories. Boeing had built the B-17E using components sourced from hundreds of suppliers, all working to the same specifications, all capable of delivering parts that would fit together properly when the aircraft was assembled. This wasn't just advanced engineering, it was advanced industrial organization, the ability to coordinate mass production of complex machines at a scale Japan had never attempted. Japanese engineers could measure every dimension of a B-17's wing structure. They could calculate the loads it needed to bear and understand how it was designed to bear them. What they couldn't easily replicate was the industrial system that could produce such wings by the thousands, consistently, with the quality control needed to ensure each one would perform reliably. The Americans weren't just building better aircraft, they had built a better system for building aircraft. This realization came gradually, through small discoveries and disappointing tests. Japanese engineers would replicate a structural design from the B-17, building their version using Japanese materials and manufacturing methods. The resulting structure would look identical, would meet the same dimensional specifications, but it would be heavier, or would fail at lower stress levels, or would require more frequent inspection and maintenance. The differences weren't huge, often just a few percent, but they accumulated relentlessly across every system and component of the aircraft. Consider something as seemingly simple as riveting. The B-17's aluminum skin was attached to its underlying structure with thousands upon thousands of rivets. American manufacturing had developed processes, specialized tools, trained workers, quality control procedures that ensured each rivet was installed correctly, creating a joint that was strong and wouldn't loosen over time. Japanese manufacturers could install rivets, of course. But without the same tools, training, and quality control, their riveting was less consistent. Some joints would be fine, others would be weak spots that could lead to cracks or failure. An American B-17 wing might have a service life of thousands of flight hours before it needed major maintenance. A Japanese copy of the same wing might need inspection and repair far sooner. Or consider something more complex, the turbo superchargers that allowed B-17 seconds to maintain power at high altitude. These devices compressed incoming air before it entered the engine, compensating for the thin air at altitude and allowing the engines to produce useful power at heights where normally aspirated engines would struggle. The principle was well understood, and Japanese engineers had experimented with turbo superchargers. But building a turbo supercharger that would work reliably required precision manufacturing of components operating under extreme conditions: high temperatures, high rotational speeds, corrosive exhaust gases. The tolerances were tight, the materials demanding, the quality control critical. American manufacturers had spent years developing the manufacturing techniques and quality control processes needed to build reliable turbo superchargers. Japanese manufacturers, attempting to develop similar devices, found that their versions worked sometimes but failed frequently and required constant maintenance. These accumulated differences meant that while Japanese engineers could understand how a B-17 worked, and even theoretically how to build one, actually building an equivalent aircraft with Japanese industrial capabilities was far more difficult than merely copying the design. The Shinzan program had already demonstrated this painful truth. Now, with actual B-17 seconds to examine, the extent of the problem became even clearer. In December 1943, reality delivered another harsh lesson. One of the captured B-17Es was preparing for takeoff at Fusa airfield when a sudden crosswind caught the aircraft before it reached sufficient speed for the rudder to maintain directional control. The bomber veered off the runway, and its right wing smashed into a parked Nakajima Ki-49 heavy bomber. The damage was severe. The captured B-17 would never fly again. The loss of the aircraft wasn't the main story. The story was what happened in the salvage and investigation that followed. When engineers examined the wreckage, they could see exactly how the B-17's wing was constructed, could trace how the loads had distributed through the structure during the impact, could understand how the design had performed when subjected to forces far beyond what it was intended to endure. And what they saw was sobering. The wing hadn't simply crumpled or broken cleanly, it had deformed and torn in ways that showed how carefully the structure had been engineered. Even in failure, even when subjected to forces that destroyed it, the structure revealed the sophistication of its design. American engineers hadn't just made the wing strong enough, they had thought carefully about how it would fail if overstressed, designing it so that failure would be progressive rather than catastrophic when possible. This attention to failure modes, this consideration of not just what a structure needed to do but how it might fail, reflected an engineering philosophy that went beyond simply meeting requirements. It showed thinking about the entire life cycle of the aircraft, about maintenance and repair, about what happened at the extremes of the performance envelope. It was the kind of thinking that came from an engineering community with deep experience, supported by research institutions, informed by extensive testing, and connected to an industrial base capable of implementing sophisticated designs. The captured B-17 seconds that remained continued to provide valuable information throughout 1943 and into 1944. They were used in training films, teaching Japanese pilots attack techniques. They helped Japanese engineers understand what their own fighters would face as American bombers began ranging over Japanese-held territory. They informed development of tactics and defensive strategies, but they also served as a constant reminder of the gap between what Japan knew how to do and what America had already done. Every test flight, every examination of the structure, every maintenance session revealed new examples of American industrial sophistication. The engineers at Tachikawa were intelligent, skilled, and dedicated. They understood what they were looking at, and that understanding made clear just how difficult the challenge would be. Despite the Shinzan's failure and the sobering lessons from studying captured B-17 seconds, the Imperial Japanese Navy hadn't given up on the concept of a four-engine heavy bomber. If anything, the early successes of the war and the deteriorating strategic situation made such an aircraft seem more necessary than ever. By mid-1942, Japan's defensive perimeter stretched across vast ocean distances. The ability to strike at distant targets, to conduct long-range reconnaissance, to interdict enemy shipping far from Japanese bases, these capabilities seemed essential to any hope of maintaining Japan's early conquests. So in February 1943, the Navy issued a new specification. This time, they would apply everything learned from the Shinzan's failure and from studying the captured B-17 seconds. The new bomber would be smaller than the Shinzan, lighter, with a more efficient wing design. It would use more powerful engines with turbo superchargers for high-altitude performance. It would carry heavy defensive armament based on lessons learned from the B-17. And critically, it would be designed from the start as a military bomber, not a converted airliner design. Nakajima, chastened by the Shinzan experience but still the company with the most experience in four-engine aircraft, received the contract. The design team, now led by engineers who had spent months studying the captured B-17 seconds, approached the project with both ambition and a more realistic understanding of the challenges they faced. They called their new design the G8N Renzan Mountain Range. The Renzan was, on paper, an impressive achievement. With a wingspan of 106 feet and a length of 75 feet, it was considerably smaller than the Shinzan, which immediately helped with the weight problem. The design incorporated a laminar flow wing, a sophisticated aerodynamic feature that reduced drag. 4 Nakajima Homare 24 engines, each producing 2,000 horsepower and equipped with turbo superchargers, promised the power needed for high-speed, high-altitude operations. The defensive armament was formidable. 6 20mm cannons in powered turrets covering all approaches, plus 4 13mm machine guns. The bomb load was substantial, up to 4 tons of ordnance. The estimated range exceeded 4,500 miles. The projected maximum speed was 368 miles per hour faster than many contemporary bombers. In every measurable specification, the Renzan represented a quantum leap forward from the failed Shinzan. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Development proceeded with remarkable speed. Nakajima completed the first prototype in October 1944, just 18 months after receiving the contract, a testament to how much the company had learned from the Shinzan program and from studying American aircraft. On October 23, 1944, test pilot Lieutenant Takeshi Matsumoto lifted the first Renzan into the air from Nakajima's Koizumi plant for its maiden flight. The flight lasted 20 minutes. Matsumoto's report was cautiously optimistic. The aircraft handled reasonably well. The engines, aside from minor issues with the turbo superchargers, performed adequately. The flight controls responded properly. There were no major problems, no critical failures, nothing that suggested the design was fundamentally flawed like the Shinzan had been. 3 more prototypes were completed over the following months: December 1944, March 1945, and June 1945. Testing continued between American air raids, which were becoming increasingly frequent and devastating. When American forces captured one of the Renzan prototypes after the war and conducted their own evaluation, their engineers reached a conclusion that would have been gratifying to the Nakajima design team. The aircraft was well designed and, in many respects, comparable to American heavy bombers then in service. And yet, despite this apparent success, the Renzan never entered production. Only 4 prototypes were built. The program was cancelled, not because the aircraft didn't work, but because by the time it was ready, Japan no longer had the industrial capacity to produce it. This is the heart of the story, the moment where the abstract concept of industrial capacity becomes concrete and devastating. Because the Renzan's failure wasn't a failure of engineering or design, it was a failure of the entire industrial ecosystem needed to support advanced aircraft production. Consider what it took to build a Renzan. Each aircraft required approximately 40,000 individual parts, not counting fasteners. These parts needed to be manufactured to precise specifications, often from specialized alloys. They needed to be delivered to the assembly plant at the right time, in the right quantities. Workers needed to assemble them correctly, following complex procedures. Quality control needed to ensure that each aircraft met specifications before it left the factory. In 1943, when the Renzan program began, Japan might have been able to manage this. The industrial base was strained but still functioning. Factories had skilled workers. Supply chains, though stretched, still operated. Raw materials, though increasingly scarce, could still be obtained. By late 1944, when the first Renzan flew, the situation had deteriorated dramatically. American submarines had effectively cut Japan off from its sources of raw materials in Southeast Asia. The naval blockade meant that rubber, oil, bauxite for aluminum production, and countless other materials were no longer reaching Japanese factories in adequate quantities. B-29 Superfortress bombers had begun their systematic destruction of Japanese industrial capacity, targeting aircraft factories, engine plants, and the infrastructure that supported them. The Nakajima Koizumi plant, where the Renzan was being built, came under attack. Workers spent as much time in air raid shelters as on the assembly line. Skilled craftsmen were being drafted into the military or reassigned to more immediate priorities, like repairing combat aircraft or building fighters to defend the home islands. The supply of aluminum and light metals needed for aircraft construction had become critically short. What supplies existed were being allocated to fighters' smaller aircraft that could be produced in larger numbers and were desperately needed for defense against the American bombing campaign. Even if Nakajima could have overcome these obstacles and begun production, there remained the question of the engines. The Homar 24 engines that powered the Renzan were among the most advanced ever developed by Japanese industry. They were also temperamental, difficult to manufacture, and required skilled maintenance that was increasingly hard to find. Each engine needed a turbo supercharger, and Japan had never successfully mass-produced reliable turbo superchargers. The few that had been built for the Renzan prototypes were handcrafted by skilled technicians, each one requiring extensive adjustment and testing. The idea of producing these engines and turbo superchargers in the quantities needed for even modest Renzan production, say, 5 aircraft per month, was fantasy by 1945. The factories didn't have the materials, the skilled workers were unavailable. The quality control systems needed to ensure reliable engines couldn't be maintained under bombing and material shortages. And even if engines could somehow be produced, there remained the question of fuel. The Renzan required high-octane aviation gasoline, and Japan's oil refineries were being systematically destroyed by American attacks. In May 1945, with one Renzan prototype destroyed in an American air raid and the war situation becoming increasingly desperate, the program was officially cancelled. The 3 remaining prototypes were hidden in dispersed locations, protected as much as possible from bombing, preserved more as technological artifacts than as weapons that might still be used. And this brings us to the central revelation, the truth that Japanese engineers had been confronting gradually throughout the war, but that became undeniable by 1945. Japan had entered a war that would be decided by industrial capacity, and Japan's industrial capacity was simply not adequate to the task. This wasn't a matter of Japanese engineers being less skilled than their American counterparts. The men who designed the Renzan were brilliant. The test pilots who flew it were brave and capable. The factory workers who built the prototypes were skilled craftsmen. The problem was that engineering skill, piloting courage, and craftsmanship, while necessary, were not sufficient. Modern warfare at this scale required something more. An industrial base that could produce complex machines in large quantities, consistently, with quality control maintained even under the stress of wartime conditions. Consider the numbers. In 1944, the United States produced nearly 100,000 aircraft of all types. Japan produced 28,000. But even these raw numbers don't capture the full disparity, because they don't account for the sophistication and capability of the aircraft being produced. The average American aircraft rolling off production lines in 1944 was more capable, more reliable, and required less maintenance than its Japanese equivalent. A B-17 Flying Fortress represented perhaps 10 times the industrial effort of a Zero fighter, and America was producing B-17s by the thousands. The disparity extended beyond just aircraft. American factories produced the high-octane fuel these aircraft needed, and produced it in quantities that seemed almost absurd to Japanese planners. American shipyards launched aircraft carriers faster than Japanese shipyards could repair damaged ones. American arsenals produced ammunition in quantities that Japanese logistics officers found incomprehensible. The entire American industrial economy had been mobilized and reorganized for war production, and the scale of that mobilization was simply beyond what Japan could match. Japanese engineers understood this intellectually by studying documents and reports. They understood it more viscerally by examining captured American equipment and seeing the evidence of sophisticated manufacturing in every component. But perhaps they understood it most completely when they tried to replicate what they had studied and discovered how many obstacles stood between understanding a technology and actually producing it at scale. The captured B-17 seconds, sitting at Tachikawa Airfield, were masterpieces of American engineering and industrial capability. Japanese engineers could fly them, could take them apart and study every component, could understand exactly how they worked. What they couldn't do was build an equivalent aircraft in the quantities needed to matter strategically. The Shinzan had failed because it was fundamentally a flawed design, an attempt to copy without understanding. The Rensan had succeeded as a design, but failed because the industrial base needed to produce it had already been destroyed. This distinction matters because it reveals something about the nature of industrial warfare. In earlier eras, warfare had been limited by immediate factors: the number of soldiers you could field, the amount of gunpowder you could produce, the food supplies you could gather. Industrial warfare added a new dimension: the capacity to produce complex machines, consistently, in large numbers, with supply chains spanning continents and coordination across thousands of factories. Japan had entered the war believing that fighting spirit, tactical skill, and operational excellence could compensate for industrial disparities. The Zero fighter seemed to prove this: a relatively simple, lightweight aircraft that could outfight more expensive, complex American fighters through superior agility and pilot skill. But this advantage was temporary, dependent on circumstances that couldn't be sustained. As the war progressed and American industry mobilized, the question wasn't whether American pilots were as skilled as Japanese pilots, or whether American aircraft were as maneuverable as Japanese aircraft. The question was whether Japan could replace its losses as fast as America could build new aircraft, and the answer to that question was obvious by mid-war. The story of Japan's heavy bomber programs, from the failed Shinzan through the captured B-17 seconds to the cancelled Rensan, traced this reality in miniature. Japanese engineers learned, adapted, and improved. The Rensan was genuinely a good aircraft, possibly as good as many American heavy bombers then flying. But as good as wasn't enough when you could only build 4 prototypes and your opponent was building thousands. After the war, when American technical intelligence teams swept through Japan documenting what remained of Japanese industry, they found the surviving Rensan prototypes. The aircraft were carefully examined, photographed, measured. 1. Was eventually transported to Wright-Patterson Air Force Base in Ohio for detailed study. American engineers who examined it reached conclusions that would have been familiar to the Japanese engineers who had designed it. This was a capable aircraft, well designed for its purpose, incorporating lessons learned from studying American bombers. But those same American engineers, looking at the production facilities where the Rensan had been built, at the damaged factories and disrupted supply chains, at the quality of materials and manufacturing equipment available to Japanese industry, also understood why only 4 had been built. It wasn't that Japanese engineers didn't know how to design a heavy bomber. It was that Japanese industry couldn't produce heavy bombers in meaningful numbers while simultaneously producing everything else a modern military required, and while under sustained attack by the very heavy bombers it was trying to match. The men who had worked on the Renzan program, the engineers like Major Saito, who had devoted years to understanding heavy bombers, the test pilots who had flown the prototypes, the factory workers who had assembled them lived with a peculiar kind of frustration after the war. They had succeeded in solving the technical problems. They had created an aircraft that worked, and yet their success meant nothing strategically because the context in which they were working had already doomed the effort. Some of these men would go on to contribute to Japan's remarkable post-war recovery, applying the lessons they had learned about industrial organization and manufacturing quality. The precision manufacturing techniques that Japan had struggled to implement during the war became hallmarks of Japanese industry in the decades that followed. The understanding that sophisticated products required not just good designs, but entire ecosystems of suppliers, quality control, and skilled workers informed how Japanese companies rebuilt their industrial capacity. But in 1945, as the war ended and the full extent of Japan's defeat became clear, these lessons were still being learned at terrible cost. The men who had tried to build heavy bombers understood better than most just how outmatched Japan had been. They had seen American engineering up close in the captured B-17 seconds. They had tried to replicate it and discovered all the subtle ways that industrial sophistication manifests in actual products. They had designed what they thought was a solution in the Renzan, only to watch as the industrial base needed to produce it crumbled under the weight of sustained American attacks. The final irony is that the heavy bombers Japan tried so desperately to build would have made little strategic difference even if they had been successfully produced in quantity. By the time the Renzan flew, Japan's strategic situation was already hopeless. American forces controlled the Pacific, and American B-29s flying from bases in the Marianas were systematically destroying Japanese cities. A force of Japanese heavy bombers, even if they had materialized, would have been unable to reverse this situation. They might have struck at American bases, might have interdicted some shipping, might have given Japanese forces slightly longer reach, but they couldn't have addressed the fundamental problem, that America's industrial advantage was so overwhelming that Japan's defeat was inevitable once that industrial power was fully mobilized. The Shinzan and Renzan programs, then, stand as monuments to a particular kind of futility, not the futility of effort or skill, but the futility of trying to overcome through determination and ingenuity what could only be addressed through fundamental industrial capacity that Japan simply did not possess. The captured B-17 seconds that Japanese engineers studied so carefully were not just aircraft, they were ambassadors from an industrial civilization that had developed capabilities Japan couldn't match. This is perhaps the most profound lesson of the story, that in industrial warfare, the visible weapons, the aircraft, the ships, the tanks, are just the tip of an iceberg. Below the surface lies the vast industrial infrastructure that produces them, and deeper still, the scientific research, engineering, education, manufacturing expertise, and raw material access that makes that infrastructure possible. Japan had tried to compete at the tip of the iceberg while lacking the foundation that supported it. When Major Saito, the engineer who had watched the Shinzan's first flight in April 1941, reflected on the program years later, he understood that the aircraft's failure hadn't been a surprise to anyone paying attention. What had been surprising was how clearly the failure had revealed the true nature of the war Japan was fighting. They weren't just fighting American pilots or American tactics, they were fighting American industry, American material science, American organizational capacity. And that was a fight that couldn't be won with courage or skill alone. The wings didn't snap off during testing, as a dramatic title might suggest. The failure was more subtle and more complete than that. The wings held together, the engines ran, the aircraft flew. But none of it mattered, because by the time Japan had learned how to build a heavy bomber, Japan no longer had the industrial capability to produce one in quantities that would make any difference. The collapse wasn't mechanical, it was industrial, economic, civilizational, and that made it far more devastating than any structural failure could have been. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.